ability to give you the test at home, but I do need you to email me if you're taking the test on Thursday at home so that I can give you instructions on how to access the test. We're going to do it the same way. I'll have the blank copy for you to turn in corrections within 24 hours. Okay. Okay, does anyone have any questions on what the test will be over? Because I don't know. What is the test over? It begins on section, here's where you'd come in handy. Begins on section 4.3. Then we add 4.4, 4.5, 4.6, 5.1, 5.2, 5.3, and 5.4. And so, see if you can do this one. This is from section 4.3. So for f of x is equal to x to the fourth minus 2x squared plus 5. Give me the following. I want to know what the critical points are. I want to know where it's increasing, where it's decreasing, where its relative max is, its relative min is. I want to know the inflection points. I want to know where it's concave up, where it's concave down. And then the big finale, sketch a quick graph. On your mark, get set, go. Put that on here. That's everybody. Think you got something? Go along. All this first bit here can be done with the first derivative. So for the first derivative, I'm getting 4x cubed minus 4x. And so I'm going to factor out a 4x. And the other factor being x squared minus 1, which factors yet again. So f prime is 0 when each of those factors is 0. So we get x is 0, x is 1, x is negative 1. Those are the x coordinates of the critical points. Then we're going to check the sign of the derivative in intervals around those. So here's negative 1, here's 0, and here's 1. And I'm getting the sign of this. So I'm going to plug things into each factor. Let's see, if x is a negative 2, the first factor is negative, second factor is negative, the third factor is negative. 3 negative things multiplied together will give me a negative right there. If I plug in a negative 1/2, the first and second factors are negative, but the third one is positive. So I have an odd number of even number of negative factors. If I put in a positive 1/2, only the middle factor is negative, which makes the product negative. And a 2 for x makes everything positive. So the graph will drop, rise, drop, rise. So it increases on the interval from negative 1 to 0, and then again from 1 to infinity. It decreases to the left of negative 1, and then again between 0 and 1. Did you decide if we had a relative max? Where is it? At x is 0, right here at the top. These two guys are going to give us mins at 1 and negative 1. So far, so good? Second derivative. Go back up here. The second derivative gives me 12x squared minus 4. I suppose I can pull out a 4. And I have 3x squared minus 1. So f double prime is 0 when 3x squared minus 1 is 0, which says x squared is 1/3. X is plus and minus the square root of 1/3. We'll take the square root of 1 and get 1, and the square root of 3 on the bottom. Just make sure you get both inflection points. Anytime you solve a secondary equation, make sure you do the old plus and minus. So those are inflection points. And we're going to check the sign of f double prime in intervals around those two inflection points. I'm not sure I know how big square root of 3 is. It's about 1.7, I think. So this is a little bit in the neighborhood of a negative 1/2 and positive 1/2. But pick something clearly over here and plug it in, like negative 10. If I square it, multiply by 3, subtract 1, multiply by 4, I'm going to have something positive.
Negative 1.
Yeah, negative 1 would work. 0 gives me a negative, and then a positive. 10 gives me a positive. So we got that it's concave up to the left and to the right of the inflection points, concave down in the middle, as what this little picture up here would suggest. So from minus infinity to negative 1 over square root of 3, and then again from 1 over square root of 3 to infinity. And then it's concave down between negative 1 over square root of 3 and positive 1 over square root of 3. And so our graph should pretty much look like a W. We might just need to refine this a little bit by plugging in some points. The ones I want to plot are 0, 1, and negative 1. F of 0 is 5. F of plus or minus 1 will be the same since I have even powers. So I'd get 1 minus 2 is negative 1 plus 5 is 4. So it looks like everything's up here. Let's make this 0, 5, and make those plus or minus 1 and 4. And then somewhere in here we'll have our change in concavity at our inflection points. So we've got a min, max, min, coming down, coming up, coming down, coming up. In between these two inflection points, we said it's concave down. Everywhere else, it's concave up. So just nice, smooth, polynomial kind of curve. There's the concave up. There's the concave down. So if I put something like this on the test at that level of difficulty, I would want every single one of you to get every bit of this right. There's nothing on here to miss outside of the fact that you got to remember to do both square roots. Okay? Questions on 4.3? 4.3 are the basic ones. In section 4.4, we did some asymptotes and some limits. So let's look at some stuff from section 4.4. First, let's look at some limits. All right. So we've got x going to infinity. I've got 3x on top. X is going to minus infinity, in fact. And the square root of 4x squared plus 7x plus 2 on the bottom. Since the numerator and the denominator involve an x, this has the form of infinity over infinity, where typically we would do L'Hopital's rule, except you've been warned at what happens to expressions that have radical signs in either the numerator or the denominator. L'Hopital's rule does not work well with those. You get into that infinite loop where that radical moves from denominator to numerator with each subsequent derivative. Right? Take the derivative of square root of x, you'll get a negative exponent, which puts it in the opposite position. So we want to avoid that. We want to kind of get this by looking at the ratio of the degrees. Is this fraction top heavy, bottom heavy, or essentially the same power? They're about the same, right? The highest power of x in both the numerator and denominator, once the square root sign x on that, is going to be x to the first power. So we should get the ratio of the coefficients, except x is going to minus infinity. That's going to make this numerator hanging around negative numbers. The denominator is going to hang around positive numbers because the x is squared. And then we've got a positive number and we take the square root of it. So if the numerator is going to be negative and the bottom is going to be positive, I should get a negative 3 over the square root of 4, or a negative 3/2. Does everybody see why? If this is going to be negative, this is going to be a negative number on the top and a positive number on the bottom because of that. If you square a negative number, it's positive. Take the square root of a positive number, it's positive. So now let's find one that we can do L'Hopital's rule to. Let's try the limit as x goes to 0 from the right of x squared times 1 minus the cosine of x. I don't think we need the from the right side. That's not doing anything for us here. One minus cosine of x will go to 0 as x goes to 0 because the cosine of 0 is 1. So I have 0 on the bottom and 0 on the top. That's a good place for us to do L'Hopital's rule. Which says we take the derivative of the top and divide it by the derivative of the bottom. The derivative of the top is 2x. The derivative of the bottom is a sine of x. So I still have the 0 over 0 form. Sine of 0 is 0. 2 times 0 is 0. So we do L'Hopital's rule again. And we get 2 over the cosine of x. And now the cosine of 0 is 1. So we have 2 over 1, or 2. Okay. Questions, anybody?
Are we going to have any of the ones where it like repeats indefinitely, so you have to cut it off early?
I'm not sure I know which ones you mean.
I just remember that there were some examples with like specifically trig functions that would go into a loop.
And then you had to stop and go and try something else? Maybe we'll look for something like that. Let me see if I can find one. This one's not going to get loopy, but let's look at it. What's the behavior of this as x goes to infinity? Because? The sine approaches 0, but this is going to infinity. It has infinity times 0 is not going to be 0. Infinity times 0 is one of our indeterminate forms. But it's an indeterminate form that we can convert to either 0 over 0 or infinity over infinity. Does anybody remember how? Do something with this guy right here. Move it in the denominator as the reciprocal. Multiplying by x is the same as dividing by 1 over x and vice versa. So I'm going to rewrite this algebraically as the sine of 2 divided by x divided by 1 divided by x. So now this term in here goes to 0, that goes to 0. So we have 0 over 0, which is good news. So now we do L'Hopital's rule. So on top, we take the derivative of the sine and get a cosine. But now we have to move inside the parentheses and take the derivative of 2 over x. Think of that as 2 times x to the negative 1. And so let me put that in the cloud to show that that's what you're thinking. So the derivative is minus 2 x to the negative 2. Now downstairs, you're thinking of 1 over x as x to the minus 1. And so its derivative is minus x to the minus 2. That gives me some room to cancel. I've got an x to the minus 2, both in the numerator and in the denominator. And I've got a minus sign. So let's cancel all of this with this and that. And so that leaves us just a 2 times the cosine of 2 over x. As x goes to infinity, 2 divided by x goes to 0. So I need the cosine of 0. Cosine of 0 is 1. This gives us 2 times 1. Our limit is 2. Okay? So L'Hopital's rule didn't really come around until section 4.5. Section 4.4, we were mostly using the ratio of powers. I'll do it. Grab us another one from section 4.5. See if I can find one that coalesced one. It's wacky on us here.
I'm not talking crazy, right?
We're not crazy. Just kind of let your hair down a little bit. Maybe this will do it. Let's look at the limit. As x goes to pi over 2, say from the left, of the secant of x divided by 2 plus the tangent of x. A secant is 1 over cosine, a tangent sine over cosine. So in either of those, the cosine's in the denominator, and cosine of pi halves is 0. If you have 0 in the denominator, then things become infinitely large. So this behaves like infinity over infinity. That's the other form that lets us use L'Hopital's rule. So I want you to take the derivative of the top and divide it by the derivative of the bottom. And let's see what we get. What was the derivative of secant of x? Okay. All right, the derivative of 2 is 0. What about the derivative of tangent? Secant squared. And so we can cancel one of those secants. And that leaves us just a tangent on top and a secant of x on the bottom. So I have still infinity over infinity. And a quick check of L'Hopital's rule again. Derivative of tangent was our secant squared. Derivative of secant was secant tangent. So we get back to essentially where we were. We'll cancel one of the secants. So it looks like I'm going to flip-flop back and forth between secant over tangent or tangent over secant, both of which have the form of infinity over infinity. So now would be a good time to use your trig identities. Right secant is 1 over cosine, right tangent is sine over cosine. Flip that over and simplify. And then we just evaluate the limit as x goes to pi over 2 of 1 over the sine of x. Sine of pi over 2 is 1. So we could start out a little bit with trying L'Hopital's rule. Maybe had you gone just to trig identities at the beginning, it'll simplify out for you quicker. But make sure you have all the weapons in your arsenal. Don't just give up if L'Hopital's rule doesn't work. You can still do some other stuff. We had the indeterminate forms of 0 over 0, infinity over infinity, which take us directly to L'Hopital's rule. The infinity times 0, we had to do some algebra. And then we had the infinity minus infinity, where we had to do some algebra. Like, for instance, that one, 1 over x minus 1 over sine of x. Both the x and the sine of x are 0 when x is 0. So both become infinitely large. And we had to convert that from infinity minus infinity to either 0 over 0 or infinity over infinity by doing some algebra. What's the obvious algebra in this case? Or did I make you paranoid by saying obvious algebra?
Multiply by x sine of x.
That's right. We're going to get a common denominator. I can't just get rid of it because I don't have an equation, but I'm going to get a common denominator. So I'm going to multiply this by the sine of x over the sine of x, and this by x over x, so that I have a fraction now. The denominator is going to be sine of x times x. The numerator will be sine of x minus x. Now, sine and x are all 0 when x goes to 0. So it's still an indeterminate form, but it's in a good indeterminate form. The good kind meaning we can do L'Hopital's rule. So we take the derivative of the top, divide it by the derivative of the bottom. Here I'm going to do a product rule. So the first times the derivative of the second plus the second times the derivative of the first. But as x goes to 0, my numerator is 0, that 0, so I still have the 0 over 0 form. So what the heck, let's try it again. Derivative cosine is minus the sine. That one is as a derivative of 0. Derivative sine is cosine. Product rule here. So I'll have x times the minus sine of x plus cosine of x times 1. Now I'm going to let x go to 0, and sine of 0 is 0. Cosine of 0 is 1. This will give me a 0 here, and that'll give me a 1. So I don't have an indeterminate form. I have 0 divided by 2. Where I come from, as 0. So the algebra in infinity times 0 and infinity minus infinity just involves doing a little rearranging of terms, getting a common denominator in this case. But then we had the exponential indeterminate forms, either 0 to the 0, infinity to the 0, or 1 to the infinity. Do you remember all the steps to that? Suppose I have x raised to the sine of 3x, and I'm going to let x go to 0. So the base goes to 0, sine of 0 is 0. This has that first indeterminate form. How do we get it out of there? How do we get that exponent down? What's our tool for bringing an exponent down?
Take the natural log.
That's right. We're going to take the natural log. First, I'll make an equation of this, and then I'm going to take the natural log of both sides. And we did that because the log of something to a power can be rewritten as the power times the log of the base. Since a logarithm is not defined for negative numbers, let's come into 0 from the right. But remember again, sine of 0 is 0, but as I'm coming in from the right, the natural log gets big and negative. So this is going to minus infinity. But it's 0 times infinity again, so we've got to rewrite that as either 0 over 0 or infinity over infinity. So we put one of the factors reciprocal on the bottom. Since I have all those reciprocal identities, I'm going to put the reciprocal of the sine on the bottom. And 1 over the sine was the cosecant. And so now I have an infinity over infinity form, because the cosecant was 1 over sine, 1 over 0 becomes infinitely large. So we can do L'Hopital's rule. We'll take the derivative of the top and divide it by the derivative of the bottom. You take it up here. Derivative of the log of x is 1 over x. Derivative of cosecant is a cosecant times a cotangent. It's negative, and then the derivative of the angle gives us a 3. And so this is going to come down with the other stuff. And I'm going to have 1 over minus 3. There's the x cosecant of 3x, cotangent of 3x. Cosecant is a 1 over sine, cotangent is a cosine over a sine. And so this is 0 and this is infinite. So I can't do anything from there. This might be a good place to rewrite cosecant as 1 over sine, cotangent as cosine over sine. So now let me bring it back here. And so I'm going to have 1 over negative 3x. This is 1 over the sine. So that's going to, let's just put it here. And this is cosine over the sine. So I'm going to have a cosine of 3x over a sine squared of 3x. The sine squared of 3x is going to flip to the top. Downstairs, I'm going to have negative 3x cosine of 3x. Is that too fast in the old algebra? It gets us to a 0 over 0 form. The sine of 0, 0, and this is 0 times 1. So we do L'Hopital's rule again. Derivative of the top is the power rule, 2 sine of 3x. Bring the power down, raise it to 1 power less. The derivative of sine is a cosine of 3x. Then the derivative of the angle gives me a 3. Downstairs, we've got a product rule. So there's the first times the derivative of the second plus the second times the derivative of the first. I think we're done here because I got a 1 down here at the denominator, or at least a 3. This term is 0. This term is 0. So we have 0 over 0 plus 3. By gosh, by golly, that's a big old 0. That took a while, didn't it?
So,
Ah, very good. That's the natural log of L. And so, undo the logarithm. Our limit is 1. Kind of got lost in all the bushes there. Forgot my end result was a logarithm.
I was going to ask you if you just guess 0 instead.
Yes? It's kind of brave. How about that for an adult word for what I really wanted to say? Then I'll have to work hard to find one that limit is not 0. In case you do guess 0. What's wrong with a little work? It's not like we're digging ditches. We're actually doing mental work. I'll find one a little shorter than that. But I do need to know that you can handle the exponential, so do expect having to compute a limit using a logarithm. So that's kind of putting section 4.4 and 4.5 together. One other thing in section 4.4 was identifying these little funky places. So let's see if I can find something that does that. Let's let f of x be x to the 2/3 minus times x minus 7. First thing I want to know is see if you can find all the critical points. So take a minute, take the derivative, find where the derivative is 0. Let's find all the critical points for that one. All right, I'm gonna catch up with you. I'm gonna take the derivative of the product rule. I'm not gonna multiply it out. I'm gonna do the product rule. F prime of x is the first times the derivative second plus the second times the derivative of the first. Then I'm gonna write this with a positive exponent. So I'm gonna rewrite my expression as x to the 2/3 plus 2 times x minus 7 divided by 3x to the 1/3. So one thing you should notice is in the original function, I've got a cube root function, which is defined for all values of x. But in the derivative, I have a denominator, which is not defined for all values of x. My derivative fails to exist when x is 0. So first make a note that f prime at 0 does not exist. But here, the domain of this function is all real values of x. So something funky is happening to the graph at x is 0. There's either going to be a sharp corner or a vertical tangent line. Now, to continue finding critical points, one thing you can do is get a common denominator here by multiplying that first expression by x to the 1/3 over x to the 1/3, actually 3x to the 1/3. And then multiply that out. Both of them now have the denominator of 3x to the 1/3. This product gives me 3x. When you add exponents, you get x to the 3/3. Then I have plus 2x minus 14. So my numerator simplifies to 5x minus 14 over 3x to the 1/3. So I got a critical number at x is 0. The other critical number is where the numerator is 0, and that is at x is equal to 14 over 5. Okay? So I'm going to keep myself reminded that here's my little red flag. I've got a place where there's no derivative. Sharp corner or vertical tangent. Now let's figure out what it is by using our critical points, and I want you to give intervals, which is rising and falling. F is increasing or F is decreasing. So we're going to do the stuff with the number line, and we're going to check the sign of the first derivative. 14 over 5, and x is 0. Again, a 1/3 power is a cube root. The cube root of a negative number is negative. The cube root of a positive number is positive. So when I'm back here with negative numbers, my denominator is negative, my numerator is negative. A negative over a negative is going to give me a positive. In here I can use 1 as my test point. My numerator will be negative, my denominator will be positive. So the derivative is negative. Here I can use 8 as my test point because the cube root of 8 is a positive number. 5 times 8 is 40, minus 14 is positive. So there's my rising, falling, rising. I got that it increases to the left of 0, and then again to the right of 14 over 5, and it decreases in the middle. But I know my graph is not going to be this nice smooth graph like that. I'm going to have something funky happening at x is 0. Let's plot those points and see if we can tell. If we can't tell, then we're going to have to do the second derivative. But let's just kind of get an idea of what this graph looks like from here. I've got a max at 0 and a min at 14 over 5. When x is 0, so is y. So there's my max. 14 over 5 gives me a positive number here, but a negative number here. So let's just put a point right there. So I need my graph to rise, fall, rise, and I need it to have the fact that f prime does not exist here, but f prime is 0 here. So can you see how that's going to happen without having to employ the second derivative? Yes or no?
It's going to come to a point at 0.
Which means it's probably going to be concave up here and then concave up here. I bet we find that our graph is concave up everywhere. Right? There won't be a second derivative at 0 if there's not a first derivative at 0, but it should be positive everywhere. And you might want to check that with the function rule, but I don't want to do that. There has to be a sharp corner in order for that derivative to fail to exist. Okay? Can you do something like that? Is that something you can handle?
Hopefully.
Hopefully. Hopefully. Okay, so I've spent a little bit too much time on 4.4 and 4.5. Section 4.6 were the applications. So let's try, say a box with no top and a square base. Is to have a volume of 1,000 cubic centimeters. What should the dimensions of the box be so that its surface area is a minimum? This is section 4.6. I wonder if I can fit the solution in that little bitty space right there. State the objective, write the objective function. If it has too many variables, write to a side equation involving that 1,000 cubic centimeters. Get your objective function in terms of one unknown, and then rock out the next one. It doesn't look square. I'll label mine with X, X, and Y. And the open top. So to get the surface area of this, we've got the bottom plus the four sides. And the bottom is what's the square, so I have an X squared here. Each side has dimensions X by Y, so 4XY. That's our objective function. And it has too many variables. So over here we can do the side equation. How do you find the volume of a box? What's the volume of the box, whether it has a top or not? Length, width, height. So here I got X, X, Y. So X squared Y is 1,000. Looks like Y is going to be 1,000 over X squared. So that's going to go here. And let's see what damage you can do to it from there. There. And we got that much room, so make sure you're efficient. All right, I got to catch up with you. We're getting run out of time here. Surface area is going to be x squared plus 4x times 1,000 over x squared. So I get that surface area is x squared plus 4,000 divided by x once I cancel. Now the derivative. I get a 2x here minus 4,000 over x squared. When I set that equal to 0, I'll move the 4,000 over x squared to the other side. So I'm going to multiply by x squared. I get 4,000 is 2x cubed. Divide by 2. So I get x is the cube root of 2,000. Cube root of 1,000 was 10, so I can say that x is 10 cube root of 2. And then you want the surface area. So the dimensions, you need 10 cube root of 2 centimeters by 10 cube root of 2 centimeters by 1,000 over 10 cube root of 2 squared centimeters. Okay? Goofy numbers, but I'll try to come up with better ones. But the other ones you need to look at are the ones where we have a rectangular field with the fences down the sides, or maybe no fence on one side because of a river or something. Or we had volume and surface area of a right circular cylinder, some version of this, but we have a container that open or closed. Or maybe I can put costs associated with this. Maybe I say the cost of making the bottom is $5 per square foot, and the cost of making each side is $2 per square foot. So it's essentially this with the cost numbers mixed in, and you want to minimize cost. Okay? So look over the ones we did in class. Now that's chapter 4. In chapter 5, I want you to be able to compute the basic integrals, whether they're definite or indefinite. I think most of you can do all these by now, but let's just look at maybe 3 of them. All right, can you do those 3 right there? No, you don't have a product or a quotient rule, so you have to break up the quotient by breaking this up into 3 fractions. So we're integrating 1 plus 1 over x minus 2x to the negative 1. Then you can integrate term by term. Oops, that's 2x to the negative 2, sorry. Integral of 1 is x. 1 over x is our special one. That's the natural log of x. Here we'll add 1 to the power, divide by the new power, and then tack on a plus c. So some version of that, x plus the natural log of the absolute value of x plus 2 over x plus c. You can break up a denominator if there's a single term, but not if there's a sum. The 6 doesn't matter. I can pull it out in front. That's one of our special integrals. What function has as its derivative 1 over 1 plus x squared? Anybody recognize it? It is an inverse tangent. Next one's a definite integral. You start by finding the antiderivative of e to the x. The integral of e to the x is e to the x. And then you evaluate that between the endpoints. Oops, that's a 3. Top limit goes in first. What is e to the natural log of 3 going to give you? 3. E to the 0 is 1. So that integral is 2. You should also be able to use some given information to find the constant of integration. I might give you a velocity function and tell you what its position is at time t, or find position at time t if you know its initial position. That kind of thing. So be able to do a problem where you have to find the constant of integration. And so, if you got a book, I'm referring to something like, example 7 on page 330. Then in section 5.2 and 5.3, I want you to be able to find a left sum, a right sum, and then find the area as the limit of a Riemann sum. And then find the area as a definite integral. Also in this section, you should be able to use the properties of definite integrals. One of them on WebWork, be able to use the properties of definite integrals.
That's crazy. Yeah. Wow. There's that. He's over her.
And so we had I put some examples on your WebWork there, like if the integral from 2 to 4 of some function is equal to 20, given, and the integral from I don't know, 1 to 4 of f of x is equal to 15. What is the integral from 1 to 2 of 3 times f of x plus 6? Is that something you can do? So here we have the linear property of integrals. I can write that as a 1 to 2, 3 times f of x dx plus the integral from 1 to 2 of 6 dx. If I know the integral from 2 to 4 is 20, and the integral from 1 to 4 is 15, then the integral from 1 to 2 has to add to the 20 to give us 15. So the integral from 1 to 2 has to be a -5. Agree? And so here I've got the integral from 1 to 2 to be a -5. Integral of 6 is just 6x from 1 to 2. So I get -15 plus 12 minus 6. So negative 15 plus 6 is negative 9. Something like that. In section, I think that may have come from section 5.4. Let me see where those properties of definite intervals are. Yeah, that's section 5. Yeah, I don't know. In section 5.4, I want you to know the first fundamental theorem of calculus. And the second fundamental theorem of calculus. We did the first fundamental theorem of calculus right here when you find the antiderivative and plug in the endpoints. The second fundamental theorem of calculus essentially says that the art or the process of taking a derivative is the inverse of taking an antiderivative. That those two operations cancel each other. So for instance, if I want to take the derivative with respect to x of the integral, say from x to 2 of, I don't know, 3 times the square root of 1 plus t squared dt. Let's even make this a more compound function. Let's make this x to the 5th so that I can use the chain rule. The second fundamental theorem says that if the lower limit is a constant and the upper limit is a function of x, you should get the integrand back as a function of that x. So the first thing I need to do is change the order of integration. And when you change the order of integration, it changes the sign of the integral. That's one of our properties of integrals. Now I'm using the second fundamental theorem that says that this operator and that operator cancel each other out, and we'll get minus 3 times the square root of 1 plus the upper limit squared. The upper limit was x to the 5th. The chain rule says now I take the derivative of x to the 5th. Okay, that's a function of x. So the derivative kills the integral and gives you back the integrand, but if the upper limit is a function of x, you multiply by its derivative. Okay. And I think that's what you asked about earlier, about doing a derivative of an integral. And so there will be something like that on there as well. So there's plenty of practice problems on the review sheet, and there's a big old fat book that goes with this course. There's plenty of problems in there. So let's spend about the first hour and 20 minutes with the test, and then we'll take the last hour doing integration by substitution. Bueno? All right. Again, those of you at home, please let me know if you have to take the test at home, and I will give you instructions on how to do that. Questions, anybody at home?
On this one, wouldn't you have to do the chain rule on the x to the 5th to the 2nd? Wouldn't you have to multiply it at the end by 2x to the 5th?
No, you're taking the derivative of this right here, not this. You're taking the derivative of the limit. The second fundamental theorem calculus says that the derivative with respect to x of a constant to a function of x of some function of t dt will give you the integrand as a function of x times the derivative of this. Has nothing to do with what this looks like, only what this looks like. Oops. So that's why I just had the 5x to the 4th. Only what the upper limit looks like. Okay?
Okay, so we don't really care what f of t is.
We don't care what's in here. We just make a composite
put
function.
the x in. Okay.
That's right. That's right. Anybody else have anything to ask? Okay, I'm cutting you down.